Welcome back to Global Works TV, where we continue our journey into the industries that shaped America and the technologies that keep building our future. Today, we take a close look at one of the great traditions of the Pacific Northwest and beyond, the wood products industry. For generations, the forests of Oregon and the American West have provided not only timber, but also livelihoods, stability, and opportunity for countless families. It is an industry remembered by older generations, respected by today's communities, and still vital to the economy and character of the Pacific Northwest. What makes this history so remarkable is not just the raw lumber that was produced, but the innovations that came later, innovations that transformed wood into products that could do far more than any single tree ever could. Among the most important of these advancements is laminated veneer lumber, known simply as LVL. LVL is not ordinary lumber. It is a carefully engineered product created by peeling thin veneers from logs, drying them, coating them with strong adhesives, and pressing them together under heat and pressure. The result is a billet of wood that is straighter, stronger, and more reliable than traditional sawn lumber. Builders can count on it for consistency. Architects rely on it for long spans and dependable strength. And families across North America trust it, often without realizing, in the beams and headers that frame their homes. Here in Oregon, this story continues at West Fraser's LVL plant in Sutherland, a community with deep ties to forestry and wood manufacturing. The Sutherland facility is one of the cornerstones of West Fraser's engineered wood operations in the United States. Day after day, trucks loaded with Douglas fir and other regional species arrive from sustainably managed forests. These logs are carefully selected, unloaded, and prepared for a journey that will transform them into high-strength LVL used throughout the country. West Fraser also operates a major LVL facility in Quesnel, British Columbia, Canada. While smaller in number, these Canadian operations complement the production in Oregon, strengthening supply chains and extending the company's reach across North America. The process always begins in the woods. Crews working in carefully managed stands fell and prepare the logs, loading them onto trucks designed to carry massive loads safely down winding forest roads. It is a scene familiar to generations of Oregonians. Trucks rumbling along highways, their trailers stacked with freshly cut timber. This is the beginning of a process that links forest to factory, and factory to the homes, schools, and businesses of everyday people. As we follow these logs from forest to mill and from mill to finished product, we will see not only the machines and the methods, but also the enduring values of resourcefulness, efficiency, and stewardship that define the American wood industry. This is the story of West Fraser LVL in Sutherland, Oregon, and part of the larger story of how wood continues to build our world. At the heart of every engineered wood product lies the forest, and the transformation begins here, at the bucking station. West Fraser's LVL facility, located 27 kilometers southwest of Rocky Mountain House, Alberta, receives a steady flow of timber harvested from managed woodlands, overseen by Sundre Forest Products, the parent mill. These forests are carefully planned and harvested under principles of sustainability, ensuring that today's production never compromises tomorrow's resources. Upon arrival at the yard, logs are unloaded by large grapple machines and front-end loaders, then placed on the infeed decks of the bucking station. This station is a marvel of automation. Guided by sensors and computer systems, it measures each log for length, diameter, and straightness. The term bucking refers to cross-cutting the raw logs into shorter sections, optimized for peeling into veneer. Every decision at this stage affects recovery downstream. A log cut too short means wasted fiber. A log cut too long will not fit the peeling lathe. Precision ensures efficiency. In 2014, the Rocky Mountain House Mill consumed about 213,000 cubic meters of logs, producing nearly 1.9 million 8-foot peeler blocks. Each block is destined to become thin sheets of veneer, and later, high-strength LVL beams. This first step represents more than cutting wood. It is where forestry, technology, and tradition meet. The work of fallers in the forest, the skill of log haulers on mountain roads, and the precision of mill operators all come together at the bucking station. Here, the log is no longer just timber. It becomes the raw material for engineered lumber that will span roofs, support floors, and frame homes across North America. Water vats. Heating the blocks softens the wood fibers, making them easier to peel into thin sheets. This step is essential because veneer must be uniform, flexible, and free of cracks. The Sutherland LVL plant is more than just machines. It is also a community. In 2014, the facility supported 150 direct jobs, providing steady work for families in Douglas County and contributing millions to the local economy. After heating, blocks are lifted by conveyors into the roundup lathe, which removes any remaining bark and trues the surface. The cleaned blocks are then carried to the spindleless veneer lathe. Unlike traditional machines that grip each end, the spindleless lathe rotates the block with rollers while a long knife peels it into a continuous ribbon, much like unwinding a roll of paper. The veneer is sliced to about 1/8 of an inch thick. Thin, uniform, and flexible, these sheets are the essential ingredient of laminated veneer lumber. The scale of production is staggering. In 2014 alone, 103,077,000 square feet of veneer were peeled here. That is enough to cover thousands of football fields, a measure that shows both the volume of timber processed and the efficiency of the machinery. The lathe is a symbol of technological progress in wood manufacturing. Earlier generations cut boards directly from logs, limited by knots, grain, and irregularities. Veneer peeling removes those limitations. Each sheet is consistent in thickness and grain alignment, making it ideal for engineered products. For many employees, this machine embodies the transition of the industry. Where once logs became rough-sawn planks, now they are transformed into precise components for products with predictable strength. It is the very definition of engineered wood, harnessing the natural strength of the tree, but improving it through technology. The endless ribbon of veneer from the lathe cannot be used as is. It passes to the clipper, a high-speed cutter that slices the sheet into standard 4x-8-foot panels. At the same time, the clipper scans for defects, trimming out imperfections and checking moisture levels. This ensures only usable, uniform sheets continue downstream. Clipping is more than just cutting, it is quality control. A missized or defective sheet would compromise the strength of LVL. By standardizing veneer dimensions here, the mill lays the groundwork for reliability in every finished beam. From the clipper, veneer sheets flow to the stacker, where automated arms and bins organize them by grade and moisture level. Operators can perform random pulling, removing off-grade sheets that will not meet LVL standards. Some of these sheets are still valuable. Instead of being discarded, they are bundled and sold to plywood mills. This step ensures that nothing goes to waste, and every sheet finds a productive use. The stacker is therefore both a sorting station and a crossroads, directing material toward its highest and best use. Cuts are sent to the chipper, which reduces the wood into small pieces. In 2014, the mill sold 48 million square feet of veneer to affiliated plywood mills in Quesnel, Williams Lake, and Edmonton, while also sending 26,500 oven-dry tons, ODT, of wood chips to the Hinton pulp mill. One oven-dry ton equals about 2,000 pounds of wood at zero moisture, a standard unit for measuring pulpwood. Cores are trimmed by a pointer-domer machine, which shapes them for resale. In 2014, nearly 950,000 cores were produced, bundled, and shipped either to Sundre for further treatment or directly to the market. Bark, sawdust, and trimmings, collectively called hog fuel, are sent to the energy plant. In 2014, the Sutherland facility consumed 14,000 ODT of hog fuel, most of it coming directly from the bucking station. The on-site energy plant has a capacity of 40 million BTUs, enough to keep veneer dryers and other equipment running. This closed-loop system shows how sawmills and LVL plants make use of nearly every part of the log. The carefully sorted veneer sheets now enter the dryer, one of the largest and most energy-intensive machines in the mill. Inside, temperatures reach about 400 degrees Fahrenheit. Sheets pass through on conveyors, spending roughly 3.5 minutes traveling from infeed to outfeed. Drying serves two vital purposes. It reduces moisture content to the exact level needed for bonding, and it stabilizes the sheet to prevent warping. Veneer that is too wet will not bond properly with adhesive, while veneer that is too dry may crack. Precision is essential. In 2014, this facility dried 84.4 million square feet of veneer. Imagine this scale: endless ribbons of wood traveling through heated chambers, each one destined for use in LVL. The dryer is a reminder that engineered wood is not only about machines, but also about careful control of natural variables: moisture, temperature, and fiber. Employees monitor gauges and sensors, ensuring that each lift of veneer exits within specifications. The work is technical, but also requires an experienced eye. Decades of practice have taught mill workers to recognize the subtle signs of veneer that is ready: the color, the sound, even the feel. After drying, sheets pass through scanners that measure density and moisture content. Density indicates strength, while moisture ensures proper glue curing. Based on this data, veneers are sorted into grades. The highest grades move on to LVL production, while lesser grades are sold for plywood. This separation is critical. Only the strongest and most uniform veneers will form the outer layers of LVL, guaranteeing structural reliability. The next step is the press line, where veneer sheets become laminated veneer lumber. Veneers are arranged into specific recipes, depending on the grade of LVL being produced. Each layer passes under a glue curtain, coating the surface with adhesive before moving to the layup station. Here, sheets are overlapped and aligned so that grains run in the same direction, maximizing strength. By the time the layup is complete, stacks may be 15 layers thick. The line feeds into a continuous press, which can run an entire shift without stopping. As veneer enters, it passes through microwave units that activate the adhesive, followed by hydraulic rams applying up to 300 pounds per square inch of pressure. This combination of heat and pressure bonds the sheets into solid billets. In 2014, about 57 million square feet of veneer, equal to 1.8 million cubic feet of LVL, were pressed here. The billets are massive, later cut to lengths between 20 and 60 feet. The press is the moment of transformation, where thin, fragile sheets become structural beams capable of carrying the weight of homes, bridges, and buildings. It represents the marriage of natural material and modern engineering. From the press, billets are lifted by cranes and carried to the beam and header line. Here, gang saws cut them to customer-specified dimensions. Employees inspect boards on the grading deck, trimming defects, applying wax to the ends, and stamping grades directly onto the surface. LVL is produced in strength classes, such as 1.3E, 1.8E, 1.9E, and 2.0E, where E refers to the modulus of elasticity, the stiffness of the beam. Builders rely on these ratings to choose the right product for the right application. Most often, LVL beams serve as headers above windows and doors, or as beams spanning long distances in new homes. They are favored because they do not twist or warp, and they provide consistent, engineered performance. Markets are balanced. About 50% of production stays in Canada, while the other 50% ships to the United States, primarily to the Midwest and Eastern regions. Wherever they go, these beams carry the reliability of West Fraser's manufacturing and the legacy of forestry communities on both sides of the border. This completes our journey through the LVL process, from forest to finished beam. Along the way, we have seen how every fiber is used, how technology refines nature, and how jobs and communities are sustained. West Fraser's LVL plants in Alberta, Oregon, and British Columbia stand as symbols of progress in North America's wood industry. But this is only the first half of our story. As we leave the world of laminated veneer lumber, we turn to another Oregon pioneer, D.R. Johnson Lumber and Wood Innovations. In Riddle, Oregon, this company produces mass timber products, glulam and cross-laminated timber, CLT, that are reshaping skylines and redefining how wood is used in modern construction. Join us as we explore the future of American timber. Now we turn from Alberta back to the Pacific Northwest, to the timberlands of Oregon, and to one of the most remarkable family-owned companies in the American wood products industry, D.R. Johnson Lumber and D.R. Johnson Wood Innovations, located in Riddle, Douglas County. A heavy-duty Kenworth T800 logging truck rumbles down the rugged forest roads of the Pacific Northwest, hauling massive logs securely chained on its trailer. These trucks are built to handle steep grades and winding curves, carrying loads that can exceed 40 tons. The logs themselves are immense, many measuring over 30 inches in diameter and stretching more than 40 feet in length. Their sheer size is a reminder of Oregon's rich timberlands and the legacy of sustainable harvesting in this region. Upon arrival at the log yard, a Cat 988 wheel loader, a machine weighing nearly 50 tons on its own, grips the logs with powerful hydraulic arms and carefully places them onto the in-feed conveyor. From here, the transformation begins. The first step: debarking, the removal of rough outer bark to expose clean, workable wood beneath. Debarking may sound like a simple task, but it is one of the most essential steps in modern sawmilling. Bark must be removed before logs can be cut, since it carries grit, soil, and even small stones that could quickly dull saws or damage equipment. At D.R. Johnson, logs roll from the in-feed deck into a mechanical debarker. Rotating arms fitted with hardened steel tips strip away the outer bark, while preserving as much wood fiber as possible. The process is quick, efficient, and ensures that only clean, sound logs continue down the line. From the debarker, the now smooth, round logs are directed toward the cut-up line. Here, they are trimmed into manageable lengths, depending on their diameter and straightness. Each section is cut to optimize future recovery, typically in 16 to 20-foot segments that will fit efficiently into the head rig. This initial breakdown is critical. The way logs are cut here influences how much usable lumber can ultimately be recovered. As the cut sections move forward, The mill's operators keep a watchful eye, ensuring that each log is handled correctly. Large diameter Douglas fir, prized for its strength and straight grain, is often set aside for beams or timbers, while smaller logs are routed toward boards and dimension lumber. Every piece of wood has a purpose, and D.R. Johnson has spent decades refining how best to unlock the value hidden inside each log. The bark and trimmings don't go to waste. They are collected and transported to the mill's residue system, where they are either chipped for pulp, ground into hog fuel for biomass energy, or sold for landscaping mulch. This philosophy of full utilization has long been part of Oregon's sawmill tradition. Use every part of the log, leave nothing behind. With the logs now cleaned and cut to length, the next stage is precision scanning. Each log passes through a laser scanner system, a technology that has revolutionized sawmilling in recent decades. The scanner creates a three-dimensional digital model of the log in real time, measuring diameter, taper, sweep, and any irregularities. Advanced software then calculates the optimal cutting pattern, the way to saw the log that will yield the maximum volume and highest value of lumber. Once the pattern is determined, the log is fed toward the primary breakdown saw, a massive bandsaw or circular saw that delivers the first cuts. The result is a squared-off timber called a cant. This step transforms an irregular, round log into a form that can be further processed with precision. For the sawyers at D.R. Johnson, it is the moment when raw forest material begins to reveal its future as beams, studs, or panels. Now we turn from Alberta back to the Pacific Northwest, to the timberlands of Oregon, and to one of the most remarkable family-owned companies in the American wood products industry, D.R. Johnson Lumber and D.R. Johnson Wood Innovations, located in the small town of Riddle, Douglas County. For decades, this mill has been a cornerstone of the local economy, transforming logs harvested from Oregon's forests into high-quality lumber and pioneering engineered wood products such as cross-laminated timber. The scene begins with a Kenworth T800 logging truck, its trailer stacked with massive Douglas fir and hemlock logs, each often measuring more than 2 feet in diameter and stretching over 40 feet in length. The heavy load rumbles down the rugged back roads of the Pacific Northwest before finally arriving at the log yard. Here, a Cat 988 wheel loader, one of the most powerful in its class, swings into action. With its wide grapple, the machine lifts the giant logs from the trailer and sets them gently onto the infeed deck, ready for the first step of processing, debarking. The freshly sawn boards are now cut to their final lengths. Long conveyors carry them toward automated trimmers, where each piece is precisely cut to standard sizes 8, 10, 12, or 16 feet, depending on grade and intended use. This is where the boards begin to resemble the lumber that contractors and builders will recognize on job sites across America. But before they can leave the mill, each board must be graded. Experienced graders, supported by scanning technology, assess every piece for knots, grain slope, and other characteristics that influence strength. Boards are then directed into different bins according to their grade. High-grade boards may be destined for structural framing, while others find use in industrial applications, pallets, or remanufacturing. Moisture content is another key factor. Many boards are routed through the kiln drying system, where carefully controlled heat reduces their moisture to a level that ensures stability and prevents warping once installed. Kiln-dried lumber is lighter, stronger, and more predictable, qualities that builders depend upon. This stage reflects the craftsmanship and attention to detail that has defined D.R. Johnson for decades. Even as automation plays a larger role, the human element remains vital. Graders bring knowledge that only experience can provide, ensuring that the lumber leaving Riddle, Oregon carries both the efficiency of modern production and the reliability of traditional sawmilling. With boards cut, dried, and graded, the final step is sorting and shipping. Stacks of finished lumber are assembled by automated stackers, wrapped for protection, and labeled with grade stamps that certify their quality. Forklifts move the bundles into neat rows in the yard, where they await shipment. From here, D.R. Johnson's lumber travels across the Pacific Northwest and beyond to regional distributors, construction sites, and engineered wood facilities. Each bundle represents not just the work of the mill, but also the forest lands that supplied the logs and the community that has supported the company for generations. The process closes the loop, from rugged mountain forests to the rumble of a Kenworth hauling logs, to the skill of sawyers and graders, to stacks of finished boards ready for use. D.R. Johnson lumber embodies the tradition of Oregon's timber country, efficient, resilient, and forward-looking. As the mill gates close on another day's production, one thing is clear. Every log has been transformed with care, every board has a purpose, and every worker plays a part in carrying forward the legacy of this remarkable family-owned company. A venerable giant, a symbol of resilience and timelessness, succumbs to the dual forces of fire and human intervention. This video documents the solemn moment a colossal giant sequoia, one of the largest living organisms on Earth, is brought down. June 3, 2021, in the heart of Alder Creek Grove, a towering sequoia with a massive 14-foot diameter was felled by Tulare County personnel. This ancient tree had been reported to be still smoldering from the devastating September 2020 Castle Fire. The prolonged, lingering burn created a significant risk, compelling authorities to make this difficult and final decision. The process of felling such a monumental tree was a challenging and labor-intensive undertaking. It took a dedicated team of professionals 10 hours of continuous work over 2 days. They meticulously used chainsaws to carve a large, wedge-shaped cut into the base of the tree, a precise technique crucial for guiding the tree's fall and ensuring it lands in a predetermined safe zone. The air was filled with the roar of the saws and the scent of fresh wood, a stark contrast to the quiet grandeur the tree had embodied for centuries. After the initial cuts were made, the crew attempted to pull the tree down with a pickup truck, but the cable snapped repeatedly, unable to withstand the immense weight and stubbornness of the old growth. Each snap was a reminder of the sheer power they were up against. Finally, after extensive and strategic cutting, the great tree began to lean. With a deafening crackle of splintering wood and a deep, earth-shaking rumble, it surrendered. A colossal cloud of dust erupted upon impact, a final, poignant exhalation marking the end of a life that had spanned centuries. The sound of its fall echoed through the forest, a sound both of finality and release. While a somber sight for many, the video notes that loggers, county staff, USFS employees, and onlookers celebrated the tree's descent. This seemingly paradoxical reaction can be interpreted as a sense of relief from the imminent danger the tree posed, and a recognition of the hard work required to safely manage such a powerful force of nature. It also underscores the complex relationship between human society and the wild forests, where sometimes intervention is necessary for the greater good and to prevent future harm. This giant sequoia may no longer stand tall against the sky, but its story, captured in this footage, serves as a powerful testament to the enduring legacy of these magnificent trees and the delicate balance we must maintain to protect them. It's a humbling reminder that even the mightiest among us must at some point yield, and in doing so, they leave an indelible mark on the landscape and in our collective memory. Its lumber may go on to serve a new purpose, but its spirit will forever be part of the forest it called home. The video you've linked documents the hazardous removal of 2 massive hemlock trees. These trees, partially uprooted and leaning precariously against each other, pose a significant risk. The felling process is a meticulous and dangerous task. A skilled logger begins by making a precise horizontal cut into the base of the first tree, followed by an angled cut. With a final crack, the tree falls, but not alone. It pulls the second tree down with it, a perfect double drop. This controlled felling demonstrates the expertise required to manage such risks, turning a dangerous situation into a successful, safe outcome. The logger begins by creating the directional face cut with a chainsaw. This critical first step determines where the tree will fall, a decision that requires both experience and knowledge of the terrain. The sound of the saw is a rhythmic hum against the quiet backdrop of the forest. He then moves to the opposite side to make the back cut, the final cut that will sever the tree. The video captures the tension of the moment as the logger works with focused determination. The camera holds on the tree as it begins its slow, powerful descent, a creaking protest giving way to a thunderous roar. The sound of the tree crashing through the undergrowth is immense. A cloud of dust and debris billows up as the giant hits the ground with a final, earth-shaking thud. The scene is both destructive and beautiful, a testament to the raw power of nature. The video concludes with the logger walking over to the fallen giant, trimming a large limb from the trunk, and then beginning the process of bucking the trunk into smaller, more manageable pieces. It's a complete look at a timeless craft, showing the journey of a tree from a towering giant to its final useful form. In this video, a logger expertly fells a towering, old-growth Douglas fir in Oregon. The video shows the methodical process as the logger uses a large chainsaw to make a precise notch at the base of the trunk. With skill and care, the final cuts are made, and the massive tree begins to crack and fall. A cloud of dust and debris rises as the ancient giant meets the ground, a powerful reminder of the raw forces of nature and industry. The process begins with the methodical work of a lumberjack using a chainsaw to carve a large, precise notch into the tree's base. His partner stands by, shovel in hand, ready to clear sawdust and debris, a testament to the teamwork required for such a dangerous task. The rhythmic roar of the chainsaw continues as the logger deepens the cut, each pass bringing the tree closer to its inevitable fall. At one point, he stops cutting and places his hand on the trunk, feeling for the subtle vibrations that signal the final moments before the tree gives way. The tension builds as the two look up, anticipating the exact moment. And then, it happens. The massive tree begins its slow, powerful descent, a creaking protest giving way to a thunderous roar. It crashes to the ground with an immense thud, sending a cloud of dust and leaves billowing into the air. It's a powerful and humbling sight, a perfect display of a timeless craft in one of America's most iconic timber regions. The challenge of a leaner is something every logger knows. A leaning tree, pulled by gravity, requires immense skill to fell safely and precisely. This video captures that very challenge, as a logger tackles a massive, leaning tree on the west coast. The process begins with the critical face cut. The logger uses a chainsaw to carefully carve a horizontal notch into the trunk, followed by an angled cut to create the wedge. This is the directional cut, the blueprint for the tree's fall. With the face cut complete, he moves to the opposite side to make the final cut. The air fills with the roar of the saw, and the sound of cracking wood signals the moment of truth. The tree begins its controlled, powerful descent, guided by the logger's work. It falls perfectly, creating a clear path through the forest. The video ends with a shot of the stump, a silent testament to the logger's expertise. The clean, flat surface shows just how much skill is required to bring down a tree so large and so prone to falling uncontrollably. It's a humbling display of a difficult and dangerous craft. The raw power of the Pacific Northwest forest is on full display as a logger prepares to fell a formidable Douglas fir. The tree, standing over 200 feet tall, presents a unique and dangerous challenge. It has a significant side lean, pulling it in an unpredictable direction. This is a task that requires not just strength, but an intimate understanding of physics and the behavior of wood. The process begins with the face cut. With the rhythmic roar of the chainsaw, the logger meticulously carves a deep, horizontal notch into the trunk, followed by a precise angled cut. This wedge, once removed, will determine the exact direction of the tree's fall, a crucial factor when dealing with a leaner. Every detail matters, and the logger pauses to carefully survey his work before moving to the next stage. He then moves to the opposite side of the tree to begin the back cut. This is the felling cut, the final act that will bring the giant to the ground. He carefully saws through the massive trunk, and the creaking of the wood signals that the tree is beginning to give way. As a safety measure and to aid in guiding the fall, he inserts a felling wedge into the cut, preparing to drive it in. The tension is palpable as the tree begins its final slow descent. The powerful forces of gravity and the tree's natural lean are finally overcome by the logger's skill. With a final, thunderous crash that echoes through the forest, the towering fir meets the ground, a testament to the timeless craft of logging and the respect required for such a powerful and unforgiving environment. In a landscape scarred by fire, where the air still holds the scent of smoke, the resilience of the Australian bush is a powerful sight. But even a forest in recovery holds danger, and here, a logger is tasked with felling a fire-damaged giant. The tree, weakened by the intense heat, stands as a testament to the devastating bushfires that swept through Victoria. The video captures the methodical process of the feller. With a powerful chainsaw, he carves the base of the trunk, the roar of the saw breaking the silence of the burnt forest. Every move is precise. Every cut is a calculated decision to bring the tree down safely. After the final cut, the massive tree begins its descent. It falls with a thunderous crash, sending a cloud of charred leaves and dust into the air. It's a somber but necessary moment, ensuring the safety of the area while honoring the life of the tree. The scene is a stark reminder of the immense power of nature and the quiet strength of those who work to manage its aftermath.